So I'm going to start chapter 20. I think it's chapter 20. Oof. 21. And so today's topic is just going to be about the nucleus. So atomic nuclei are made of protons and neutrons, of course. And in nuclear chemistry, we're going to name things a little bit differently. So protons and neutrons are now called nucleons. And an atom is called a nuclide. Hold on a second. Let me minimize you guys because it's distracting. Okay. All right. There we go. So a nuclide is identified by the number of protons and neutrons in a nucleus. So it's not just about atomic number, but it's also about atomic mass as well as atomic number. Because atoms are made of protons, neutrons, and electrons, you would expect the mass to be the same as if you added up all of the protons, neutrons, and electrons, but that turns out not to be the case. So I'm going to look at a specific example of helium. And also notice that in the notation, in the atomic symbol, now we use both atomic number and atomic mass. Okay, so breaking down the mass of helium. Helium, we have 2 protons. Each proton has an atomic mass unit of 1.007276. So that gives an AMU for the protons of 2.014552. Then we take the neutrons, same thing, multiply it times the AMU of a neutron, and we get 2.017330. And finally, the electrons, which have an AMU of 0.00054886. And when we add all of that together, the collective mass of all of the parts of a helium atom ends up being 4.032979 AMU. If we compare that to the atomic mass of helium, the atomic mass is 4.00260. So it's actually 0.03038, less than the calculated mass. Oops. There we go. Okay. Right. So if you add up the parts, like I said, the 2 protons, 2 neutrons, 2 electrons, you add all of those masses together, you get more mass than what the actual mass is. And so this is called mass defect. It's the difference between the mass of an atom and the sum of all of the atom's parts. I'll get to why there is a loss of mass in a minute. Okay, but just for now, understanding that atoms, I don't know why my, what do you call it? The mouse pointer thing disappears when I'm in full screen. That's really annoying. Okay, so again, what causes that loss in mass? So we can go back to Einstein's equation, E equals mc squared, that says mass can be converted into energy and vice versa. So mass defect is actually caused by the conversion of mass into energy when the nucleus is formed. And I want to bring a parallel to what we learned in chemistry in grade 10, which is when you break bonds, like in a chemical equation, when you break old bonds, you have to put in energy, but when new bonds are formed, it releases energy. Do you guys remember that, hopefully? So bond breaking is endothermic and bond formation is exothermic. So taking the second part, the formation being exothermic, applies the same way to the formation of a nucleus. Again, energy is released when the nucleus is formed. So the mass units of the mass defect can be converted to energy using Einstein's equation. So basically what that means is you can calculate how much energy is going to be released when the nucleus of a helium atom is formed by using E equals mc squared. So the mass defect that we have for helium, which was 0.03038, We're going to convert that to kilograms to match the unit for energy. So we take the AMU, and I actually had to look up this morning because I was like, what the heck is that? I didn't understand in my mind where that conversion factor came from. And it really is just a conversion factor like we've learned for 3 years. So just for 1 atomic mass unit, it's equal to that many kilograms. So we use that conversion factor to change AMU into kilograms. Now we have mass, and we can just plug that into Einstein's equation. So we get E equals that mass we just calculated times C, which is constant. And so we end up getting 4.54 times 10 to the minus 12 joules. Is everybody with me so far? Did I lose anybody? I will take silence as a yes. Like, yes, everybody's okay. Okay, everyone's okay. So we just calculated, thank you. We just calculated the amount of energy that accounts for the loss of mass of a helium atom, okay? And so what this energy represents is something called nuclear binding energy. It literally represents the energy that's released when that nucleus is formed. So again, bringing a parallel back to what we learned in grade 10, when we learned how much energy is released, for example, to form, let's say, a mole of water, the energy that's released is going to be the same energy that's required then to break the bonds in that molecule, right? So I don't remember what the specific number is. I think it's 286, but I can't be sure. Let's just say it's 286. So let's say 286 kilojoules per mole of energy are required, or sorry, are released when water is formed. That means that 286 kilojoules of energy per mole are required to break down water. So that's the same thing here. If 4.5 times 10 to the minus 12 joules of energy are released when the helium nucleus is formed, in order to break the nucleus of a helium atom, you would need 4.5 times 10 minus 12 joules of energy. Okay so far? Okay, thank you. I see ice with it. Thanks. Okay, so again, like I said, it can also be thought of as energy needed to break apart the nucleus. It is also, just like we studied in bond formation and bond breaking, the more energy that's released, meaning the more energy required to break the bond, is kind of an indication of how strong the bond is. So nuclear binding energy is also an indication of how stable the nucleus is. Okay, so the more energy that's released, the more stable the nucleus is. Okay, I'm gonna take this out. If this works, I'll play the sound through my computer and hopefully you can hear it. If it sucks, I'll just stop and we'll move on.
Consider the Earth and a rocket ship, which are bound together by gravity. If it takes work or energy to pull them apart, then the binding energy is the amount of energy it takes to completely separate them. Similarly, the binding energy in a nucleus is the amount of energy it takes to completely separate the protons and neutrons, collectively called nucleons. There are two forces acting inside the nucleus of atoms. The nuclear force, a residuum of the strong force that holds quarks together, is pulling the neutrons and the protons together, and the electric charge on the protons is pushing them apart. The strong force is a lot stronger than the electric force at short ranges, up to 2.5 times the proton diameter. But at larger distances, the electric force dominates. So as we add nucleons and work our way up the chart of the periodic table, initially each nucleus is generally a little more tightly bound than the one before. This chart gives the actual numbers. This increase in binding energy continues until we get to iron and nickel, where the nucleus has about 60 nucleons in it. At this point, the nucleus has a radius more than 2.5 nucleons wide. which you remember is the range in which the repulsive electromagnetic force begins to dominate. So as we add nucleons past this point, the electric force trying to tear the nucleus apart starts winning, and each added nucleon is a little less tightly bound. When we get to lead and bismuth, and the nucleus contains 207 nucleons, the electric force wins, and the atomic nuclei larger than this are unstable and come apart by themselves, although it may take a while. These larger nuclei can return to more stable arrangements in several ways. They can convert neutrons into protons and give off beta radiation, or kick out whole groups of nucleons, 4 at a time, and alpha radiation. Or they can simply split into other smaller, more stable nuclei. When this happens, we call it fission.
Okay. How was the sound for that? Was the sound okay? I'm guessing it's okay because nobody's talking. Awesome.
All right,
It's
but
okay.
still like hard to hear a little bit.
Hard to hear a little bit? Okay, I'll see if I can make that better in the future. I want to go back
Okay.
and kind of cover what he talked about anyway. So over here, he was talking about how there's two forces at work on the nucleus. You have this, the S, called a strong force. Without getting too complicated, it's basically the fact that when protons and protons are really close together, they actually are strongly attracted to each other. Same thing with neutrons and neutrons. So that's like the attractive force. It only works at very short distances. And then you have the repulsive force on the other side, which is the electrostatic force that comes from the charges. So protons and protons are positive. They don't like each other. So the point is that you've got these two fighting forces in the nucleus. So when we come to this graph, his point was basically as you add more nucleons to the nucleus, the nuclei become more stable because you have more of these strong forces that are holding the nucleus together until you get to iron. When you get to iron, now the size of the nucleus becomes basically the limit of the attractive forces for the strong force. So basically after iron, the nucleus becomes bigger than the distance where the strong forces overcome electrostatic forces. So past iron, you see the graph start decreasing because as you add more nucleons to that, the electrostatic force of repulsion wins over the strong force of attraction. And that's why you see the stability go down. Then when you get to really high nuclide sizes, that's when they become very unstable. And then when he was talking about at the end, there's different ways for atoms to become more stable. And that's what we'll talk about when we talk about nuclear decay. So sometimes they can throw off like a beta particle and a proton becomes a neutron. And sometimes they can throw off like an alpha particle. There's just different ways that we can make a more stable nucleus. But I just wanted to show you that because the focus of this section is really looking at what holds a nucleus together. So does all that make sense? So it's going to be kind of an ideal range of size of nucleus, and until you get to that point, the nuclei are quite stable. Once you get larger than that, then they become unstable. Okay, so binding energy per nucleon is the binding energy of the nucleus divided by all of the nucleons that it contains. And the higher the binding energy is, the more tightly the nucleons are held together. Again, nucleons are both protons and neutrons, everything in the nucleus. Elements with intermediate atomic masses have the greatest binding energy per nucleon, so they are the most stable. Okay, so like medium-sized atoms. Now, for the nuclides that are stable, they have certain characteristics. When the number of protons in stable nuclei are plotted against the number of neutrons, you get what's called the band of stability. And if any of you have the book, if even you have the book, the graph that the guy talked about in the video is on page 642. That's the one where it's like the binding energy and the stable nucleus. And then once you get past a size that's too large, it starts going down, which means your nucleus is becoming less stable. And then, oops. On page 643, that's where you have the band of stability. Okay. So yeah, there it is. What this graph shows you is there's a very delicate balance between the ratio of neutrons to protons. And I want you to look at the, here we go. Keep forgetting I got my iPad here. So looking at this line on the left-hand side, the neutron to proton ratio is 1.5 to 1. And on the right-hand side, the neutron to proton ratio is 1 to 1. And all of the stable nuclei lie between these two ratios. There's a very, very narrow range of neutron to proton ratio where the nucleus will be stable. So for low atomic numbers, most stable nuclei have a ratio of about 1 to 1. And you can look at helium that I talked about at the beginning is an example, which at atomic number 2, atomic mass of 4. So it has 2 protons, 2 neutrons. Oxygen's another one because oxygen is number 8 and it has a mass of 16. So again, it has 8 protons and 8 neutrons. Carbon as well, 6 protons and 6 neutrons. All of these that are in the low range have a ratio of 1 to 1. So as atomic number increases, we're going to increase from a ratio of 1 to 1 to a ratio of 1.5 to 1. And remember, the 1.5 is for neutrons, 1.5 neutrons to 1 proton. Examples of the 1.5 range are around lead, which has 124 neutrons and 82 protons, 1.5 to 1. So again, going back to that strong nuclear force versus electrostatic force between protons, it's the relationship between a pull by the protons and the neutrons, and the electrostatic repulsion between the positively charged protons. So the protons in the nucleus repel other protons. That's the electrostatic repulsion. But the nuclear force is very short range, so it only affects protons that are close to them. As the number of protons in the nucleus increases, the electrostatic force between protons will increase faster than the nuclear force. It goes along with that same graph that we saw before, which was like you had this really stable and then it goes, it starts coming down again. So at higher atomic masses, you need more neutrons to increase the nuclear force and stabilize the nucleus. Beyond bismuth, which is atomic number 83, the repulsive force of the protons is so great that you don't have any stable nuclides after bismuth. Okay? All right. So again, characteristics of stable nuclei. Stable nuclei have even numbers of nucleons. Of the stable nuclides, more than half of them have both even protons and even neutrons. Only 5 nuclides on the entire periodic table have odd numbers of both. And this shows that the stability is greatest when nucleons are paired. I should have put the chart further up. Here we go. So this kind of explains it a little bit better. So on the right-hand column here, this is the number of nuclides. And you might think, okay, well, the first number up there is 163. But the periodic table only has 118 elements. So how the hell do you have 163? Well, remember that nuclides defines all atoms of every element, which includes isotopes. So every atom that's in existence is part of this table. So when protons and neutrons are even, you can see of all of the known isotopes of every element that exists, almost like, what is that? I don't even know what got to be like 2/3 maybe, because the rest of them's like 100 and something. Yeah, maybe 2/3. I don't know, or 60%, whatever. But most of them are have both even numbers of protons and even number of neutrons. When you have even protons and odd neutrons, the number of stable nuclides drops down to 53, and about the same number if you have odd protons and even neutrons, about 50. But when both the number of protons and neutrons are odd, there's only 5 nuclides in existence that are stable. So basically, even numbers are good, odd numbers are bad. So most stable nuclides have 2, 8, 20, 28, 50, 82, or 126 protons, neutrons are total nucleons. These are basically what are called magic numbers. And the only thing that I can kind of think of as an analogy is when we learned about electron stability, right? When we learned about the levels of the energy levels where electrons can exist, right? Like you used to learn like 2, 8, 18, 36, or 32, like that. Those were like the magic numbers for electrons. So if an atom has 2 electrons, it's stable because the first level holds 2. If an atom has 8 electrons, it's stable because level 1 can hold 2 and level 2 can hold 6 for a total of 8. Remember that? Remember that? Like a full octet. So the magic numbers are basically like an octet, but for the nucleus. So these particular numbers just provide extra stability. And we call it the nuclear shell model, which is basically a reflection, or not a reflection, but it's like a nucleus version of the octet rule. Maybe I can say that. Right? So nucleons exist in different energy levels or shells in the nucleus, and those numbers represent those shells. Everybody okay so far? So we've got even numbers are good, and these are the magic numbers. So atoms that have protons and neutrons or total nucleons that are these numbers are the most stable. Okay, so what happens if you don't have a stable nucleus? You go through what's called a nuclear reaction. Now, for this chapter, we basically don't give a crap about electrons. We're only really looking at the characteristics and the makeup of the nucleus. So remember bismuth, number 83, is kind of the last stable nuclide. After that, they're unstable. So after that, we go into unstable atoms, which go through nuclear reactions. So there's going to be different versions depending on what the nucleus does to make itself stable. I think that's the next section, which I'll talk about later. But a nuclear reaction is any reaction that changes the nucleus. So here's an example of something called, well, not something called, but this is an alpha particle here. Boop. So when we have a nuclear reaction, it follows the same rules when we had a chemical reaction or even a redox reaction. Everything on the left-hand side has to equal everything on the right-hand side. So if you have a reaction like this, you have to make sure that all of the masses, all of the masses here add up and down here as well. Sorry, I'm like covering half of it, but you know what I mean. So all the numbers on the top have to equal all the numbers on the bottom. And of course, if the atomic number changes, the identity of the element changes, and that's called transmutation. So in this example, we have a beryllium atom that absorbs an alpha particle and turns into a carbon atom and releases 1 neutron. So because we have changed the atomic number, which is always on the bottom, it's gone to 6. So in a lot of the nuclear reactions, I don't know if I'll start, probably I'll start that this week, but I got a couple of worksheets to practice like mass defect and band of stability, which we'll work on a little bit later. But when you start working with nuclear reactions, you'll probably be adding the atomic numbers and atomic masses first, and then going to your periodic table and figuring out what element that is. You're not going to write this probably until last, because if the identity of the nucleus is changing, then of course you have to figure out what the new atomic number is going to be before you identify the element. Does all that make sense? I hope. Basically, the idea of transmutation is just if you have an unstable nucleus, it's going to go through changes to make it stable. And we're not getting into what those changes are yet, because there's like, I think 4 or 5 different reactions that a nucleus can go through. But I think that's all.